Hello, and welcome back to another video. This time, I'll be touching on something more complex, radiation processes. However, this is a very big topic, so it'll be split into at least 4 parts. Today's part involves continuum emission, and more specifically, thermal or blackbody radiation. So, I'll give a short introduction on what it is, and then dive deeper into this thermal or blackbody radiation. So, continuum emission is the type of emission of electromagnetic radiation that produces a range of wavelengths rather than spectral lines. And it includes the blackbody radiation we will talk about today, but also something called free or bremsstrahlung radiation, and also cyclotron and synchrotron radiation, which are all going to be discussed in further episodes. Here you can see the difference between several spectra, and the top one is what we'll be discussing today. On a slightly unrelated note, you probably all know that a prism can split light into basically a rainbow, and how it does that is part of something called geometric optics, which is actually another video I'll be doing soon. Now let's get into the specifics of thermal or blackbody radiation. Essentially, it's the light emitted by an object that absorbs incident radiation, with a perfect blackbody being something that absorbs all incident radiation, which of course doesn't exist, but there are some things that are very close to it. For example, stars are a very good blackbody. On the left here, you can see a blackbody curve, which shows the intensity of light emission at different wavelengths and different temperatures. You can see that at very high temperatures, the peak intensity occurs closer to the blue at visible wavelengths, while the lower temperature, the peak intensity drops and slides to the red, and eventually infrared. This is why we have such things as blue supergiant stars, which are extremely big, bright, and hot, while there's also red dwarf stars, which are very small, cool, and dim. The equation for intensity as a function of temperature and wavelength is this, where h is the Planck's constant, c is the speed of light, lambda is wavelength, k is the Boltzmann constant, and t is temperature, all in SI units. To find the wavelength in which intensity will peak, we can use 2.8978 times 10 to the negative third power meter Kelvin divided by temperature in kelvins. Now, you may be wondering, if the peak of these blackbody curves can occur at all wavelengths, why are there no green or purple stars? Well, this is the answer, the Planckian locus. It shows the path of color an incandescent blackbody will follow in a particular chromaticity space. This one is modeled with CIE coordinates XYZ, and it covers all colors the human eye can see. And so for the XYZ coordinates of a specific blackbody, we use the integrals shown here, where m is the spectral radiant excitance, which can be calculated using almost exactly the same equation to the one that models the blackbody curve. Finally, I've been saying that a star is a really good blackbody, and if you're wondering how good, this is the spectrum of the sun compared to the spectrum of a perfect blackbody at the same temperature, which are really close. However, the best blackbody is the universe, which you can see here, following the blackbody spectrum basically exactly the same. Oh, and as a final note, the blackbody spectrum doesn't have to be intensity as a function of wavelength and temperature. It can also be of frequency and temperature, which if you put on a logarithmic scale will look like this. And you can find the peak frequency by using this equation. So this is all I'll be talking about today. If you enjoyed it, don't forget to like and subscribe. And if you have any questions, please comment below. Thanks.